So let's start. Today we're happy to have Fabian Haiden from Center for Quantum Mathematics, probably one of the unique in the world in Denmark. And he will speak about counting in Calabi-Yau categories. This is the first lecture from the mini series. There will be one more in a week from now. Fabian, please.
Yes, thank you, Jan. Thank you very much for the invitation. I'm happy to speak here again. So this week and next, the plan will be this week will be more background, introduction, talk about the kinds of problems that I want to solve. And then I'll go more into the details of how to actually solve them next week. So this is about my joint work with Mikhail Gorsky that's now on the archive since posted last year. It's kind of a longer paper, 70 pages or something. So we're doing several things, and it's really nice to have 2 hours so that I can give you all the background and more of the details of what we're doing. So what's the plan? First, it's really central is this idea of homotopy cardinality. So I'll talk about what that is, if you've not seen it before. And what is it used for? And in particular, 2 areas that I'm going to focus on are whole algebra, not polynomials. So uses of homotopy cardinality in those subjects. Then I'll talk about some situations where you would really like to have homotopy cardinality, but it's because of some infinities, it's not really well defined. But you still expect some kind of generalized notion of homotopy cardinality, which will have some expected properties. And this project is kind of about finding those. So we develop some kind of formalism which allows us to extend the usual definition of homotopy cardinality. And then using that, we develop some applications to whole algebras and not polynomials. And I think there's probably many other applications as well. I'm going to talk about some possibilities in geometry and algebra. All right, so start with what is this term homotopy cardinality? Well, first of all, maybe what is groupoid cardinality, which is a special case. So if you have a groupoid, and it should be very finite in the sense that it has a finite set of isomorphism classes of objects. And also, for any 2 objects, the set of morphisms between them is finite. So the most finiteness you could hope for from a groupoid. And then the groupoid cardinality is, well, it's not exactly the number of isomorphism classes, but each isomorphism class is weighted by 1 over the size of its automorphism group. So if take a sum over all isomorphism classes, and for each of them, Hom makes it so these are the automorphisms, which we're assuming is finite, and then 1 over that, taking the sum, so we get some non-negative rational number. And I'm going to denote that by kind of the cardinality of G. Of course, you could also define this cardinality of G just to be the number of isomorphism classes. But the point is that somehow this, even though the definition looks more complicated, is actually easier to compute than the raw unweighted number of isomorphism classes. That's because, this kind of equation that the cardinality of the quotient is just the quotient of the cardinalities, where here X is a set, G is a group, everything is finite. But this X mod G, it's not the quotient set, but it's the quotient groupoid, or it's called action groupoid, right? So it's, you can think of it as the isomorphism classes in this groupoid will correspond to orbits, and then these automorphism groups in that groupoid will correspond to the stabilizers of the group action, right? And whereas the number of orbits could depends on exactly how G acts on X. This cardinality, groupoid cardinality, I don't need to know anything about the action. I just depends on the size of X and the size of G. So that's why I'm saying it's actually easier to compute, or even perhaps more natural from some perspectives, even though it looks more complicated. You could ask, why not just use the number of isomorphism classes? All right.
It's true. Some of our students are studying stacks right now. So it's this kind of a stacky function if X quotient G is as a stack.
Yeah. So in some sense, you could say, well, if you have a stack, then that's also a groupoid.
But here,
for each field, you get a groupoid. But it will be infinite, right? So if you have a stack, and
in
you
that
look
case,
at
it's not a rational number, but whatever the sum makes sense.
Yeah. So that there's like more elaborate versions of this where you count in motives and not just kind of number of points over a finite field. Yeah, this is somehow, think of this as a stack maybe for geometrically minded people.
Yeah, thank you.
Yeah, but so far X is just a set, so no stacky structure. So stack assumes some algebra geometric data.
Yeah, it's not a stack, but a stack would, if you look at its FQ points, would give you an example of such a thing. All right. So
yes, this is a trivial stack.
It's not a stack, Zhongzhu, unless
each point is a point with automorphisms. Discrete.
Yes. Yeah, but now I want to go to actually something that's more like higher stacks. Or maybe before I do that, I want to just mention something. So this is not really an example of what I just told you because you have an infinite number of isomorphism classes. But if you take the category, or the groupoid rather, of finite sets and bijections between them, and so now you have infinitely many isomorphism classes corresponding to integers, but everything converges in this case. So 1 over the size of the automorphism group, that's 1 over the size of the symmetric group. You get a sum 1 over n factorial, and you get Euler's number. So Euler's number is the groupoid cardinality of the category of finite sets, which is, I don't know, just a cute fact, I guess. Yeah, but now I want to go to higher groupoids or homotopy types. So groupoids correspond to homotopy types which don't have any higher homotopy groups. So for pi2, pi3, and so on, all vanish. How does that correspondence work? Well, if I have a homotopy type or a space, I can take its fundamental groupoid, gives me a groupoid. And in the other direction, if I have a groupoid, I can take it kind of classifying space. So that's more familiar if you have a single group. Then you have the groupoid BG with one object and whose automorphisms are that group. And then the classifying space is something whose pi1 is that group, right? And you can do that also for groupoids. Given a groupoid, you can construct some space whose pi0 and pi1 are as specified. Right, but now instead of just looking at homotopy types who have sort of the first two steps in the Rapostnikov tower, who have only pi0, pi1, you could look at arbitrary homotopy types. Yeah, now there's some kind of problem with terminology that some people call them infinity groupoids, which I'm told is old-fashioned terminology. I'm calling them homotopy types. And what's known as the homotopy hypothesis says that these two are the same. Some people just say spaces, which can be also a bit ambiguous. Space is a lot, or more recently, anima. So all these things mean the same thing, essentially, or maybe are different models for the same thing. But we assume that we have one of those homotopy types. And again, we need some very strong finiteness. So we need that all the homotopy groups are finite, and we need them to vanish for or be trivial for big enough I.
So
and then
again,
the following,
for people who see it for the first time in their life, so so you just said that several definitions mean the same thing, but you didn't say what either of them means intuitively, how people should kind of
So,
Great
yeah,
students
that's a good
should
question.
imagine
So,
what's a homotopy type. Yeah.
a homotopy type is the space, a topological space. But when I say homotopy type, I sort of want to emphasize that if you give me another topological space and the two spaces, there's a continuous map between them, which induces an isomorphism on all the homotopy groups, then that they are both as good as the other. So in particular, homotopy equivalent spaces are the same homotopy type.
Or you can students think that was a simplicial set?
Not yet. Yeah, if you want, you can also have simplicial sets here, but the easiest thing is probably to just here replace this word homotopy type by topological space. And then I'm writing homotopy type instead of topological space because I only care about the homotopy groups in some sense.
Yeah, thank you.
Yeah. All right, and so we're going to assume all this finiteness, and then you can sort of generalize the previous formula where now you take an alternating product. So here we're taking the sum over all components of this x. And for each component, we're taking 1 over the size of pi1 times the size of pi2 divided by the size of pi3 times the size of pi4 and so on. Right? And at some point, this is not really an infinite product by our assumption that these are eventually trivial. So it's just really just a finite product. So what we get in the end is some rational number. Okay, so this is homotopy cardinality. Yeah, it was kind of also goes under other names like multiplicative Euler characteristic and was kind of reinvented several times by different people. Yeah, actually, so when I gave this talk at IGS, afterwards, Maxim Kontsevich pointed out to me that he wrote this definition at some paper of his from the 90s, and this is the earliest known kind of in a paper published definition that I know of. Okay, how is this used? I mean, yeah, again, maybe it has a nice property with respect to like a vibration. So if you take what generalizes this previous fact about quotients. Now, if you have a Serre vibration or something of spaces, you have a long exact sequence of homotopy groups, then you get some formula for these homotopy cardinalities. Okay, yeah, where do we see this applied in mathematics? So some places that I know of are, well, first of all, for defining topological quantum field theories, particularly extended ones. And basically, I'm not an expert on TQFTs, but one of the cases is there's something called Dijkgraaf-Witten theory, where your gauge group is just a finite group. So you look at maps from your space into a finite group, or rather into the classifying space of a finite group. So it's some kind of toy model for Chern-Simons. And now you replace the classifying spaces of a finite group, e.g., by some arbitrary homotopy type. And then when you define some partition function, you're counting the sort of maps up to homotopy, then you can use this homotopy cardinality. And there's very nice properties which ensure that you get some fully extended TQFT at the end. Then it's used in defining Hall algebras of DT and A infinity categories. So this was first by Johan, and I'll discuss how he does that in more detail. And then, yeah, so Kontsevich-Sabelman, when they define their motivic Hall algebra, it's not really using this homotopy cardinality exactly in the way which I presented it, but a kind of motivic variant, a more refined motivic version of that. But I don't want to go into detail about that. But yeah, it's also kind of based on Johan's formula. A third use is in Legendrian knot theory. So I'll talk about what are Legendrian knots and what are these terms mean. But basically, there's some kind of knot polynomials, and they have an interpretation as a homotopy cardinality. So that I'll talk more about that, how that works. This is due to Ng-Rutherford-Shende-Sivek. And then this is sort of how I got into this subject. I was looking at the relation between, on the one hand, skein algebras of surfaces, and on the other hand, Hall algebras of Fukaya categories of those surfaces. And to explain that relation, you need this notion of homotopy cardinality. And this also, I'd had some previous work on that relation, and that sort of inspired also this project. Okay, so let's talk about Hall. Yeah, now I'll talk about so number 2 and number 3 in this list. And these are also applications that appear in our paper. And then the other stuff is more kind of future directions. So let's talk about Hall algebra. So the most basic definition of a Hall algebra is what's called Ringer Hall algebra. So it's some way of kind of turning an abelian category into an algebra. And how do you do that? Well, you need to assume some finiteness conditions, that the number of morphisms between any two objects is finite, and the number of extensions is finite. So if these may look a bit silly, but an example would be like representations of some finite dimensional or algebra over some finite field. So there are examples of this, typically linear over some finite field of such abelian categories. So how is the Hall algebra defined, or this Ringel Hall algebra? Well, it has a basis, the set of isomorphism classes of objects in my abelian category. And the product is defined by, if you have two objects, you look at all the possible extensions. So all the possible kind of short exact sequences, which begin with X, go to Y, and then to Z. And then you take kind of a sum over all possible extensions you get. So Y here, if you stare at this, what does it mean? It means there's a short exact sequence, X going to Y, going to Z, and then you take the sum over all of those Y, or all of those isomorphism classes. So in particular, it will include like the direct sum of X and Z, but also usually a abelian category, you have some non-trivial extension, and then it will include those as well.
So here the cardinality actually in Hall algebra, the coefficient should be the homotopy cardinality, because there are group automorphisms acting on the short exact sequences.
Right. So here somehow this set doesn't have any automorphisms. So here it is actually defined.
In abelian category, when you say the sub-object, which is not very well defined.
The sub-object is just sub-object, right? So there is like I kind of know what you mean, right?
There is a kind of a bit conflict in your notation, because you said that as a basis of isomorphism classes, but when you write the definition, you use actual objects. You know,
yeah,
you
so cannot
say
some
that
representative.
Well, actually, this is this part of the work for general abelian categories done by Green, J. Green, and the cardinality here you are writing is exactly the homotopy type, the homotopy cardinality you defined earlier. So dividing, which is for the coefficient of Y, that you are dividing the number of automorphisms, which is the automorphism of X and automorphism of Z.
Here I really don't divide. So there's two. This is something that's confusing. There's two different bases of this Hall algebra. So there's one basis which is related by the other by multiplying by the size of the automorphisms of X. And in one basis,
Zhangzhu is asking in general, there might be infinitely many isomorphic objects of X prime which belong to
well,
Y.
the issue is what does the sub-object, you're counting the sub-object X prime. That's what the counting here is.
Yeah, so what
this is a correct one if you're counting, if the sub-object makes sense.
Yeah, so I'm saying for each Y is running over isomorphism classes. So for each isomorphism class, choose
y,
some
fixed
representative.
y, you are counting the number of x primes.
Yeah, I'm saying no, if I choose some other, so y here is not really an object, but it's an isomorphism class. But if I choose some other isomorphism class, I get the same answer in this formula.
So what are you counting here?
I'm counting sub-objects.
The subject, that's the x prime you are counting, right?
Yeah, that's right.
And so the problem here for, in a specific quiver representation theory, you have a fixed space. You can count sub-vector spaces, that's fine. But when you count sub-object in a category, which is always corresponding to some morphisms, and which is
okay.
the
So you want to say,
acting
you define what does this mean in an abelian category, right?
That's right. That's the issue. Mm-hmm.
This means I have a monomorphism from x prime to y, and I identify two of those if they are intertwined by some isomorphism.
That's right.
Yeah. You're right. There's a definition of sub-object in an abelian category, and it's an equivalence class of object together with a monomorphism to y.
Mm-hmm. That's where the group, equivalence classes. That's exactly where the groupoid properties are right. Anyway, but
yeah, but here it's really not a groupoid.
You are
so
motivated
it's just
to understand
this
that.
is defined over integers.
Yes.
Yeah.
Yeah,
so here you don't need groupoid cardinality for this definition. But maybe I'll continue. But yeah. We can talk about this point more later, I guess. Okay, well, the point is this is associative because you look at, if you kind of form a triple product, then you're looking at an object with a two-step filtration, which has specified subquotients. It's also unital. The unit is the isomorphism class of the zero objects. Yeah, this is a point that's well-known kind of experts in Hall algebras. So I'll come back to this, so I want to mention it. So there's a certain twisting. It turns out that even though this definition looks very natural, in some cases, it's not actually the thing that you want to consider. But it's almost the thing you want to consider. So what you do is, well, assuming that there's only finitely many of those X groups, so they kind of your category has finite cohomological dimension, then you can define this Euler pairing. It's the Euler characteristic of the X from X to Y. So this only depends on the class of X and Y in the Grothendieck group. And then the twisted Hall algebra has a product where you just add this power of the square root of Q to the product dx. So this will still be associative whenever this thing here is just any bilinear form that only depends on the Grothendieck classes in the Grothendieck group of C and X. So there's nothing special really about the Euler form, but it turns out that somehow this normalization leads to something that's quite nice, and that's in this next theorem of Ringel, which is maybe one of the motivations you could have for why Hall algebras are nice things. So it says it establishes a relation between Hall algebras and quantum groups. So let's Q be some quiver of Dynkin type. So it's an orientation of an ADE Dynkin diagram, simply laced. And then there's an isomorphism between, on the one hand, well, not the entire quantum group, but the nilpotent part. So kind of the strictly upper triangular part in the AN case, where so quantum group is some deformation of the universal enveloping algebra of the semi-simple Lie group of that type. And it's deformed with some kind of formal parameter Q, and you set that equal to a prime power. And then the algebra is isomorphic to is you take the abelian category, which is representations of that quiver over the field FQ, and you do the twisted Hall algebra. Yeah, and in fact, they're not just as algebras, but it was later shown as kind of the whole bialgebra structure can be recovered in this way. But yeah, definitely an algebra. So yeah, why is this nice? Because these quantum groups somehow, when they were first defined, they were defined sort of by generators and explicit generators, and how you somehow some very explicit formulas, which are not very conceptual or geometric. And here we see that we can get at least half of the quantum group in a kind of very natural, conceptual way by this category. So as a kind of categorification of RepQ, FQ. So this was a very important result in this theory of Hall algebras, and also quantum groups. So later led to Lustig's discovery of these canonical bases. So he considered a sort of more sophisticated version of the Hall algebra, which is based on perverse sheaves. But this idea that quantum groups are realized as Hall algebras was one ingredient in that discovery of canonical bases. An obvious question now is, well, here we only get kind of the half or the nilpotent part, more precisely, of the quantum group. Can we somehow get the full quantum group? And the guess is, well, if you got sort of half of the quantum group from the abelian category, then maybe you can get the full quantum group if you double that abelian category. And doubling that abelian category amounts to taking two periodic complexes in that abelian category. So that a two periodic derived category. There's a little problem with that in that the isomorphism classes, if you look at isomorphism classes in the two periodic derived category, that corresponds to the kind of nilpotent part of the quantum group, and then the other half, but then you're sort of missing the Cartan part of the quantum group. But that should also somehow come in some construction, some hypothetical construction. More generally, you can ask, well, how can I define the Hall algebra of a triangulated category? So this category of two periodic complexes is an example of a triangulated category. We know by Bingham how to define Hall algebra of an abelian category. If you just take that formula for abelian categories, it still makes sense in a triangulated category, but it doesn't give you an associative algebra. So somehow you need to be a little bit more clever to come up with a definition that works for triangulated categories. And so this problem, it's now solved in many cases. So for many classes of triangulated categories, it's not clear. So I don't think that in complete generality you can. I'm saying here suitable finiteness conditions anyway, but it's not clear like what those conditions should be to ensure existence. But probably not in complete generality. You can expect this to be defined. It's been solved in many cases now, but actually this original problem. So if you start with this particular triangulated category, then its Hall algebra has not been defined in some intrinsic way. So there are some constructions, but they're based on sort of auxiliary things like exact categories and so on, like in Bridgeland's approach.
Probably I just want to quickly point out that in the triangulated categories, generalizing terms on construction, that there is a series of work by J. Shaw and his collaborators that's going to much more general triangulated categories under suitable finiteness conditions.
I'll talk about definitely Jones' work, but I think so for this category, it's not been solved yet.
Yeah. And also for the top of this two periodic derived category, even before Tom's work, instead of constructing the quantum group, full quantum group, actually using that for constructing the core and the entire universal enveloping algebra for arbitrary quiver. That work was done much earlier, even before Tom started this question.
You mean Lie algebra?
And Pan.
So you can get the Lie algebra again, there's been lots of work done.
Yeah.
Thanks for mentioning that.
Thank you.
So yeah, but so what kind of our project is based on this is this idea of Toen. Oh yeah, before that, so I'm not actually going to solve, or we are in our paper are not going to solve this problem for this particular category, but we solve a kind of similar problem. So what we're going to solve is the following thing. So take an elliptic curve, and then over a finite field, you could consider the category of coherent sheaves. That's one of those which have all these finiteness conditions, so finitely many Homs and X1s. It's a nice hereditary category. And then so from A, we can construct on the one hand the Ringel-Hall algebra. And again, it looks like sort of half of what it wants to be. And so what we can do is there's this construction. If you put the co-product on this, you can take a Drinfeld double, and then that recovers sort of the missing half of that bigger quantum group. Oops. However, you somehow expect that you can directly go from this. So here is this category of two periodic complexes. And somehow you expect that there should be some construction which takes you from this category of two periodic complexes to this Drinfeld double of the Hall algebra. And you know, why would you want that? Why not just go this way? Because then if it is an intrinsic construction, for example, it tells you immediately that any autoequivalence of this derived category, of which are much more than autoequivalences of the abelian category, will also be a symmetry of this Hall algebra. So definitely kind of you expect some kind of intrinsic way in which to fill this dotted error. And that's going to be one of the applications of the theory we develop. And this example is sort of a very special case. In general, whenever we have a odd Calabi-Yau category, which might be periodic or even less than that, degree-wise, kind of finite dimensional, we will construct some Hall algebra from that. Okay, so let me talk about this Toen's Hall algebra, which is kind of our starting point. So again, so here an assumption comes in that we don't just have a triangulated category, but it's actually the kind of shadow of a DG category, what's called a pre-triangulated DG category. And then the homotopy category of such a guy will be a triangulated category, defined over some finite field. And yeah, all the X groups should be finite. But more severely, the X group should vanish for big enough or a small enough I. So only finitely many degrees are they actually non-zero. And then here's the nice definition. So it's not actually how it defines it. So I'll say where this comes from, but this is the explicit formula for how the product is defined. And you see, again, it's a sum over all possible extensions of these objects, Z and X. Cone, this will just be the corresponding object sitting in the middle of that triangle. The weight is now more complicated than in the original formula. And the weight, it looks a bit like a homotopy cardinality. It turns out it actually comes from some kind of relative version of that homotopy cardinality. Right, but we definitely, again, this is essentially only a finite product because of this assumption here that these things vanish. Yeah, it's actually, we only need in the end that it vanishes for I very negative. It could be non-zero for I very positive, as is sort of evident from that formula, and as one can show. So Toen shows that this is associative and unital. And so I want to explain now where that formula comes from.
Why do you need DG structure to write down this formula? Just
so you don't need DG structure. Yeah, that's a good, thanks for pointing that out. Yeah, so this seemingly makes sense in any triangulated category. where you have these assumptions here, 1 and 2. And it was then later proven that actually you don't need this DG enhancement to prove associativity. I think by Zhao and Zhu or something. Yeah. I mean, like DG in practice, the triangulated categories will have some DG enhancement. All right. So yeah, I want to explain where this formula comes from, and kind of how all the formulas. This somehow also explains a bit where all the different versions of the whole algebra come from. So if you have a DG category, yeah, we want to relate DG categories somehow to homotopy cardinality. So if we want to apply homotopy cardinality, we need some spaces or homotopy types. And there's a way to go from a DG category to a homotopy type or a space. Yeah, now space is going to be Kahn complex actually, but I mean, so complex means simplicial complex satisfying some conditions. You could go from that again to a topological space. But yeah, how does that work? So, and this is some kind of now analog of if you have just an ordinary category, you could take the maximal groupoid sitting inside that. So you take only the isomorphisms in your category. That gives you some subcategory, which is a groupoid, and which is the maximal groupoid. And you want to do the same thing now for DG categories. But DG categories are really higher categories. And so one way of doing that concretely is if you have a DG category, you take what's called its DG nerve. So that's looking at functors from some version of the AN, the category of representations of the AN quiver, or the algebra of the AN quiver, to your DG category. This DG nerve constructs for you a simplicial set, which has an additional property that it is a weak Kahn complex. So this is what is called also a quasi-category by Joyal, and then infinity category by Lurie is exactly this weak Kahn complex condition. But the simplicial set satisfying some conditions in what would be called an infinity one category in more modern language. So this is just, the first step is just saying, well, a DG category is in some sense, a special case of an infinity one category. And then we want to extract the sort of maximal infinity groupoid or maximal sub-Kahn complex. We want to throw away all the morphisms which are not invertible. And then this gives us an actual Kahn complex. So what is a model for a homotopy type? I'm going to notate that by C tilde. So yeah, if you've never seen that before, the way to think about it is it's some higher categorical analog of starting with the category and just taking its groupoid of isomorphisms. And now, because we have a DG category, we'll have some higher, some kind of automorphisms and so on. But we don't really, yeah, I am not really actually going to use that construction or the details of it. What we really care is about the homotopy cardinality. So we just need to know what are the homotopy groups of this guy, and they're quite easy to describe. So the set of the pi zero, the set of components, is the set of isomorphism classes of this category. The first fundamental group at some point x, which is the same as the object of the original category, will be the group of automorphisms of x. So up to kind of homotopy. So it's sitting inside kind of x0. It's invertible morphisms which are invertible up to homotopy. And then pi 2, pi 3, and so on are the negative x groups in that category from some object to itself. So I'm forgetting like some information because I don't know like morphisms from some object to another object. That's not isomorphic to it. Okay, and then this is really all I'm going to use, the information about what are the homotopy groups.
So for our students, here you are. I see. So this is a pi. Okay, thank you. So this is the notation of X and the homotopy group relation. Yeah. Thank you.
Okay, thanks. Yeah. Right. So for a DG category, it has some kind of space or homotopy type of objects. So that's how we're going to link this notion of homotopy cardinality to DG categories. Yeah, now I'm going to assume that C is pre-triangulated. So C is a DG category that's pre-triangulated. So it means it has shifts and cones. Actually, we just need that it's closed under extensions. And then we can form a kind of span or correspondence. So at the apex, we have the category of morphisms in C. And this is something where you would run into trouble if you were working in triangulated categories. So the category of morphisms in a triangulated category is not naturally triangulated, but in DG categories, that's something that works. So this more C, the arrow category is again a DG category. And it's the same thing as the category, essentially the same thing as the category of short exact or triangles, right? Because if I have the morphism f from x to y, I can complete it by setting z equal to the cone. And in DG categories, you can make a cone functorial. And so then this has three.
I recall there was this paper by Dikerhoff and Kapranov. They developed kind of this whole algebra formalism in the framework of two Siegel spaces. And I think...
That's right. So this is somehow part of some two-sequel object, but I don't want to introduce all that.
It's a special case of that more general story. Okay. Or not?
Yes. So one perspective is that the whole algebra is something that you associate to a two-sequel space, and now I'm constructing kind of part of a two-sequel space given a DG category.
So if I remember correctly, they didn't have that problem with non-functoriality of cones, which means that morphisms didn't have the triangulated structure. I think it's still two-Siegel space. Maybe I'm mistaken.
I mean, I also don't have that problem. I'm just saying that you really need C to be a DG category, not just a triangulated category. No matter how if you call it two-sequel space or something, it's still.
Yeah, I mean, as long as you have cone as functorial, right? That's the key.
Well, for this, well, we also want associativity. So let me say I want everything to be a DG category. I mean, in some sense, I don't really care about triangulated categories, which don't have some enhancement.
Okay.
All right, so we get this. So if we have a triangle, x going to y going to c, there's kind of, we can send it either to x, to y, to c. So we get three different functors to our original DG category C. And we're just going to put two of those on one side of the correspondence. So they're corresponding to x and z. And y we're going to put on the other side of the correspondence or span. And now we can, so this is some diagram of DG categories and DG functors, and we can apply this construction from my previous slide to get a diagram of spaces. I mean, really here, Kant complexes by doing this, like taking kind of the maximal infinity groupoid thing. We get some diagram of spaces. And then the next step is that we want to linearize this diagram. So we take, what this really means is Q, I should maybe written, so this is pi 0 of C tilde. So I take rational linear combinations of components of C tilde. Yeah, I should have maybe put here a pi 0 for clarity. Just writing Q C tilde. But that linearizes the space, so it depends only on the set of components, and the product becomes a tensor product. And then what do I do with this map between Kant complexes? Well, here I just take a pullback, and the pullback doesn't depend on the homotopy groups at all, only on pi 0. But of course, to get from a finitely supported function kind of to another finitely. I'm using the fact that here this has finite fibers on the set of connected components. And then I want to push forward via G, and that will involve some kind of, that will involve the information of the higher homotopy groups. So loosely speaking, I mean, you can write down a formula, but it's the sum over the fibers weighted by the homotopy cardinality of the homotopy fiber. So if you have a continuous map between spaces or current complexes, then there's this homotopy fiber, which is the kind of homotopically correct way to define fiber. And you take the homotopy cardinality of that thing. That will be the weight that you use to kind of fiber-wise integrate a function on here to get something down here. Okay, and then you compose the two, so then you get some linear map from this tensor product to this guy. And it's nothing but it's what owns all algebra product is. So there's some explicit formula, which is the one I told you before, maybe up to some change of bases.
This product is associative, yeah?
Yes, that's a good question. So that uses some diagram, which now involves.
I'm not asking. Yeah, no, I'm not asking why it is associative.
Okay.
The question is no. The question is rather. I mean, you're working with infinity category. I mean, why? It's natural to ask for some algebra, whatever, DJ algebra, infinity algebra, because you have higher homotopy groups everywhere except of your final definition, which probably should be taking.
So you muted for a moment, Jan.
Yeah, you are muted. We cannot hear you.
Sorry. Yeah, I muted because of Zoom. Zoom muted me. No, I mean that at the time of Green and Hall, of course, people didn't know what are kind of DJ algebra or infinity, or at least they didn't use it. But why not to construct? Like whatever you say, I mean, it admits kind of motivic upgrade, so you can define an algebra object in some category, well, in motivic sense of motives here, maybe in some DG enhancement of a triangulated category, and your associative will be just taking H0, something like that. I'm just curious why I haven't seen people trying to do that seriously. Although it's very natural because you can kind of avoid maybe proving difficult associativity that ABC equal to ABC the other way. They should be just homotopy equivalent and so on, so on. Yeah.
Yeah, that's a good point. I mean, there's many flavors of Hall algebra, right? Where you always start with.
In the end, people want them to be associative. I'm just curious.
Yeah. I mean, they're always going to be associative just because this here is kind of a critical object.
Yeah.
Is the associativity more straightforward or get involved quite?
I mean, associativity of this
Kapranov discussed it about associativity. The issue for triangulated category, general triangulated category, using the distinguished triangles, counting the distinguished triangles, only when if that's the derived category of a hereditary category. So he was using Hasenberg double kind of way. So that works. Otherwise, the associativity fails.
Yes.
So here you basically said that this definition, the associativity is straightforward if the G nor shrink is defined.
Yeah, I'm saying there's a conceptual, there's like the same proof associativity for all different versions of the whole algebra, which will be some diagram that will appear later in my talk, I guess. But,
so that's similar to tones.
I mean,
Associated.
yeah.
Was also using
he doesn't
exactly
prove
this.
directly. So
yeah, the picture here looks like a tones. He was using the space of arrows, and which was the morphisms, and those. So the left-hand side is very much the same picture. The span is, of course, Tone didn't do that for the DG categories.
You mean Kapranov, or so I'm just saying here what Tone did.
In Tone's construction, Tone proved
Yeah.
associativity using this homotopy cardinality.
Yeah, so the proof I'm saying here works for DG categories, and it's in fact associativity is true also for triangulated categories, but the proof is less conceptual. Somehow.
Okay, thank you.
Yeah. Right, now I want to make a point. Yeah, this is also going to be important a bit later, that there's sort of two bases when you define a whole algebra, which are related in the classical case by this factor of the size of the automorphism group of the object. And it comes from thinking of this linear combinations, rational linear combinations of isomorphism classes, either as functions or as measures. This was a point that was actually I learned from this paper by Kontsevich and Sabelman, because their explicit formula is actually like this, but this is not actually the explicit formula you see in Toen's paper, and I'm explaining now kind of what are these two different perspectives. So, well, you can think of this either as functions or signed measures, and then, so by definition, kind of functions and measures are the same vector space, but the natural isomorphism between them is not the identity, but it's multiplication by this this function here. That's what could be called weighted counting measures. So it's just, again, kind of homotopy cardinality, the thing that appears in the homotopy cardinality. And so then when you work with measures instead of functions, instead of having this pullback and this kind of fiber-wise integration, you have this f upper shriek and f lower star. And well, they are defined in such a way that, you know, once you intertwine with this isomorphism here, which is given by multiplication with this weighted counting measure, then those become the same. So there's some commutative diagram kind of taking f upper star and multiplying with mu x is the same as multiplying with mu x and then taking f upper shriek. That's what I want to say. So it's just, and if you want, it's just a kind of change of bases, and then all your formulas will look a bit different in the other bases, but will give an isomorphic algebra. And more generally, we could, of course, take some power here and consider sort of S densities for some real number S. Yeah, for now, this is just a kind of change of bases, but it will become more important. And later when we go into our formalism, where it turns out that, for example, like one of those might be defined, but the other not. Basically because it might be that sort of this thing here is not defined, but some operations are still defined between spaces of densities. Okay, that was maybe a bit of a cryptic remark, but we'll come back to that. So the second, yeah, I hope I have 5 more minutes to talk about the genre knots, I guess.
Yes, you do, yeah.
Yeah, so this will have to be a bit quicker. So this is another example where homotopy cardinality appears. So Legendrian knots are curves in R3, which are tangent to this contact distribution. So it says that the y coordinate is the slope dz over dx. And then in that diagram, I don't need to specify if it's an overcrossing or an undercrossing, because the slope tells me the y coordinate. So given right-handed rule, it kind of has to, I know that I can recover the entire knot in a three-dimensional space just by knowing the picture here in the XZ plane. Yeah, and in this subject, you try to classify those kind of knots up to isotopy through the same kind of knots. Yeah, maybe let me ignore this. So there's a notion of grading, similar to grading in Kaya categories. And the Z-mod 2 grading is the same as an orientation of the knot. Then I think I'm going to skip explaining exactly what is a graded normal ruling, but maybe this picture here is illustrative. But the important thing is that to a Legendrian knot, you can associate some kind of knot polynomial, which I'm going to write as PL of Z. And it's counting some kind of things like this, which are called rulings. And so this is some polynomial, Laurent polynomial with non-negative integer coefficients. And it's not completely obvious, but it's an invariant up to Legendrian isotopy. So invariant up to kind of isotopy through Legendrian knots. And it can actually distinguish knots which are topologically equivalent. So they're isotopic through non-Legendrian knots, but they're not isotopic through Legendrian knots. And this was one of the first ways in which to do that in the subject. Except actually the Z-mod 2 graded version of this ruling polynomial is just part of the HOMFLY polynomial of the knot. So that's just a topological invariant. It doesn't distinguish Legendrian knots in the same topological class. Yeah, then there is some kind of category that is a DG category or infinity category, depending on how you define it exactly. That's attached to a Legendrian knot, which is called the augmentation category. And yeah, so the definition, let me maybe skip the definition. It's pretty elementary, actually. So the way we did some kind of sequence of acyclic complexes with a complete flag, finite sequence. And each time you have a crossing or cusp in your front diagram, you change that complex a bit. But the main point is the following theorem by Ng-Rutherford-Shende-Sivek. It says, take L to be a Z-graded Legendrian link. It has some augmentation category, which is a DG category, taking it over a finite field, FQ. It's a DG or A infinity, depending on how you define it. It has finitely many isomorphism classes of objects. And in fact, its homotopy cardinality, which appears here, is well-defined. And then this theorem says that its homotopy cardinality is essentially up to some power of Q, that's easy to compute, is the same as this ruling polynomial where you set your Z equal to square root of Q minus 1 over square root of Q, Q being the number of elements of your finite field over which this category is defined.
Sorry, but you're kind of faster here than maybe I wanted. But if I consider
depends on how much. If you give me more time, I can explain more, yes.
Yeah, you have.
Or we can come back to this next
slide.
time. Yeah.
Yeah, but I have a question. If your Legendrian knot kind of, I think of it as embedded into the contact boundary, for example, I don't know, the cotangent bundle to a curve. Question is rather whether I can interpret it in terms of the symplectic manifold for which the contact manifold is a boundary. Because people here are more familiar with symplectic geometry, Fukaya categories and other stuff.
Okay, that's great. Yeah, I mean, you can think of it as you take R4 and you somehow put this knot at infinity in the contact boundary R3. And then you look at filling. So you look at Lagrangian surfaces, which kind of asymptotically towards infinity approach this, this knot L. And that's not quite the same as an, so it's not quite true that every object in this category comes from such a filling, because you need like maybe immersed stuff, and yeah.
Yeah, but if you do, how?
Yeah, but if you kind of look at the Fukaya category with boundary conditions, so it's yeah, it's like Fukaya category with boundary condition, this Legendrian L. And also kind of, you have to be rank 1. So you need to hit the L with the right multiplicity. So it's not, yeah.
And
it's not
so
closed under direct sums.
And what it will be, this augmentation category or what?
It will be this augmentation category, yeah.
All right. And PL, does it have intrinsically Lagrangian interpretation?
Well, by this formula, you could say it's kind of counting these fillings, right?
Well, yeah,
Yeah.
but it's. But
I mean, all
it's
other
not,
definitions depend on some projections, right?
It's not the polynomial. It's a value, if I understand you, it's a value of this polynomial in the particular point, which depends on whatever your Q.
Yeah, I mean, you need to either look at all possible Q, or you need to upgrade and then replace Q by motive, like you do.
Okay, yeah.
But yeah, that's not really an essential issue. Yeah, the space, if you consider this kind of as a stack, really, then its motive is not so. It's like art and Tate type. So
That's the
it's a polynomial in one of.
Yeah, it's really just kind of polynomial in affine line. So
yeah, okay, and
there's no
so
other information.
And this is the polynomial, but it's a bit. I mean, a strange fact that it has non-negative integer coefficients, which of course gives some kind of direction for speculations what these coefficients are in general. So
I mean, they count rulings, right? So
yeah, I understand that technically, yeah.
Yeah.
Okay, all right.
Yeah. Right. So I don't. Yeah. So I want to say that. So if L is now Z mod 2M graded only, then the right-hand side is still, so this polynomial depends on the grading. So if your thing is Z mod 2M graded, there's another thing. It again has a ruling polynomial, which is the Z mod 2M graded ruling polynomial. But the right-hand side is defined still in this case. However, the left-hand side is not defined, again, because of these periodicity issues. So this category is now Z mod 2M periodic if L is only Z mod 2M graded. And the homotopy cardinality doesn't make sense because you have an infinite product. And it doesn't converge. However, this gives you actually some hint that maybe this thing should be well-defined because we sort of know what the answer should be, right? If we kind of say that we want something like this to be true, then we say, well, maybe there is actually secretly some definition of this thing, even though the obvious definition somehow is infinite pathological. And so again, that's one of the things that in my work with Misha, we're going to solve. We're going to explain how do you define this thing, even though this category is periodic.
Just go back
maybe
to the page here, the Q. So the homotopy cardinality of C1L, does that has anything to do with Q or not?
Yeah, so you take this, this is defined over any field, and you take it over FQ.
Okay, I see.
So I should have written something like here.
The cardinality was defined relating with the Q, right?
Well, yeah, so I should have written here L comma FQ to say it's kind of it's the version of the augmentation category over FQ. And then the cardinality of that will be this, where you plug in this prime power into the ruling polynomial. Yes.
Okay, thank you.
Okay, so yeah, maybe perhaps I'll leave it to next week to explain how we solve all those problems in our formalism. Yeah, so I guess I'm going to end it here.
Yeah, I think that it looks like the new kind of new section in your talk. So yeah,
yes, this is a natural stopping point.
Yeah. All right. Thank you very much. So more questions. He had many during the talk, many interruptions. Are there any more questions?
Yes, I do have especially for this polynomial. I mean, the PL is determined only by the length, and the C1L, which is depending on the finite field, if you take, and then you can compute the homotopy on cardinality. So what happens if you have the C1L replaced by, instead of overcomplex finite fields, but overcomplex numbers, you have some kind of a geometric space?
Yeah, that's a good question. So I should be doing some kind of more sophisticated, instead of looking at my variety over a finite field and then counting points.
Yeah.
I should do some sort of motivic version. Is the ultimate, as in Maxime and Jan's work on motivic Hall algebras, right? So over complex numbers, you would see that all the varieties of objects which appear here. So this is something called augmentation variety. It's actually just argentate. So it's kind of decomposes into C stars and products of C stars. And so it has a very simple motive, very uninteresting motive in some sense.
Actually, what I was thinking much older than motive was wave conjecture, wave philosophy. That over complex numbers, you have those spaces you can take the cohomologies of with compact support, let's say with rational coefficients. So
right. So you can take these cohomologies, and then that's actually an interesting point. So they would give you some maybe. Well, if you took the Euler characteristic of those things, you would again get this polynomial. But if you didn't do that, you would get something that's somehow more refined. So that's cohomologies of augmentation varieties, and this is a much studied subject for sure. Yeah.
Okay, thank you.
More questions? Well, if there are no more questions, so we are looking forward for your next week lecture, Fabian, and thank you very much.
The same time, right?
Yeah, same time, yeah.
Okay. Yeah, thank you. And thanks everybody for
Thank you.
coming to the talk, and I'll see you next week.